Hi, and welcome to the second video in the Measure Theory series, Measurable Spaces and Sigma-algebras. In the last video on functions, we ended by saying that functions operate only on elements of a domain set, and that if we want to know something about a group of elements, we had to transform that group into an element. And we did that in an ad hoc fashion to suit our needs. We transformed the old domain, S old, into a new domain, S new. Now we're going to do that in a more systematic fashion using rules. This leads us to measurable spaces. To keep some terminology straight, you're able to do something with this space. In the future, you'll learn a term where this thing has already been done to the measurable space, and it will no longer be able or measurable. It will just be a measure space. So this is a representation of a measurable space. Set S is like the old domain from the previous example, and set A is like the new domain from the previous example where you created new elements that were subsets of the elements from set S. But unlike in the previous example, we will generate A using systematic rules, not in an ad hoc fashion. There are formal requirements for the structure of A. The formal requirements are necessary for the mathematics used in probability theory to hold. And from now on, we'll construct A using these rules. The new domain we are creating is called an algebra. It is based on information found in the old domain, S, and it is a set of subsets. So what does that imply about the elements of A? It implies that they are all sets. Every element in the algebra A is a set. There are just three requirements in generating the algebra A. The first requirement is that the original set, S, is an element in the newly created set. Second, the complement of any element in the algebra A will also be in A. And third, for any two elements found in the algebra A, their union will also be found in A. So if you're having difficulty interpreting these notations and concepts, then just go and review the set theory video and it'll catch you up on all of these notations. So now let's break this down. First of all the elements in an algebra are sets. Every element in the algebra is a subset of the elements in S, the old domain. It can be any subset of any size, including the subset with each and every element of S, which is requirement number 1. And it can include subsets with only one element from S, which I refer to as unit sets. Now I want you to be aware that talking about the elements in the new domain that we're calling the algebra can be confusing because every element in the algebra is a set. So I could refer to the elements of the algebra, or I could refer to the sets in the algebra and be talking about the same thing. So just be conscious of that. The next two rules in the algebra, Rule 2, we need complements, and Rule 3, we need unions. If you are creating this new algebra, set A, and you're inserting complements and unions so that you're following these rules, then you have to stop and look at the algebra that you've created and see if the new sets that you've inserted into the algebra, the complements and the unions, now need complements and unions of their own. Because every set in the algebra must also have its complement, and every pair of sets must have their union in the algebra. And you just keep doing that until you're sure that you're done. Every element in the set A has its complement and its union with another set in the algebra A along with it. Another note is that S, the old domain, is called the universal set when it's an element in A, the algebra. The fact that S is an element of the algebra A has an important implication, and that is that the empty set is also an element of A, because the empty set is the complement of the universal set S. Another implication of including all the unions and complements is that by default, the intersections of sets are included in A, and the relative differences of sets are included in A. One type of algebra is called a sigma-algebra. And to create a sigma-algebra, rules 1 and rule 2 are the same. The only difference is that rule 3 changes. For an algebra, rule 3 is that for any two elements found in the algebra, their union will also be found in the algebra. For a sigma-algebra, rule 3 is for any number of elements found in the algebra, their union will also be found in the algebra, not just for any two elements. So it could be the union of more than two elements in the sigma algebra. So how do we start constructing a sigma algebra? We can construct a sigma algebra for a domain, set S, by identifying a subset C of elements that we wish to measure, and then defining an associated sigma algebra by generating a sigma algebra on C. You get the sigma algebra with the fewest elements that also contain the set C. So if you generate a sigma algebra on C, then you know that C is in the sigma algebra. After putting the universal set in, which is rule number 1, then you put in C, and then you start taking complements and unions. The set that you start with to create a sigma algebra has to be subsets of the old domain. Here's an example. We can partition S, in this case, based on identifying two subsets. Subset A consists of elements B, C, and D, and subset B consists of elements F, G, and H. So you're ready to create the sigma algebra with subset A and subset B. You start by putting in the first element in the sigma algebra, the universal set, and that's rule number 1. Then, since subset A is in the sigma algebra, you go ahead and list that. Then you take its complement. That's rule number 2. And since subset B is in the sigma algebra, you list that. And take its complement. Again, rule number 2. Then you can take the union of A and B, and that's rule number 3. So you feel good, you've gone through all 3 rules, but remember, you need to go back and see if inserting these sets into the sigma algebra has created the need for more complements and unions. It's not just the complements and unions you see immediately from the 2 sets that the sigma algebra is being created for, but every set in the sigma algebra must have its complement also in the sigma algebra, and every combination of sets in the sigma algebra must also have its union in the sigma algebra. So as you can see, we need the complement to the union of subsets A and B, and you put that in. Then don't forget the complement to the universal set, the null set. And technically, the null set is always an element for every set. Okay, now what is subset A or subset B or the rest of domain S? Each element in set S may be, for example, physicians in zip code 14620. And subset A are the physicians that work at Strong Memorial Hospital, and subset B are the physicians that work at Highland Hospital. And elements A and E are all other physicians in the community. Why this matters is maybe not evident now, but it is important to remember that while you're learning these rules and how to apply them, eventually these skills will be applied to research design. So here's another example. We can think of these elements as physicians in a medical home. And this time we want to represent every combination of provider coordination. So we create our sigma algebra based on the most granular partition of the original set. This would be a sigma algebra where each element in the domain S is in the sigma algebra. But when they're in the sigma algebra, these elements are sets, so they're unit sets. The sigma algebra that you will generate is called the power set. The power set is a sigma algebra that includes each individual element in the original set as a unit set. When you start by putting each element from the original set into the sigma algebra, you end up with the sigma algebra with all possible subsets from the domain, or the sigma algebra with every possible combination of elements from S, the old domain. A little secret about the power set is that the number of elements in it equals 2 to the power of the number of elements in the original set. So let's go through creating this power set. Start with the original set and its complement, the null set. Then each element in the original set is in the sigma algebra, and each of their complements are in the sigma algebra. And all the unions are in the sigma algebra. So let's start with the two-way unions. And then we can go to the three-way unions. But wait, the three-way unions, such as A, B, C, are already in the sigma algebra because they're in from being the complements of the unit sets. Also, the four-way union is already in because it is S, the universal set. So you're done. We just made a power set. Next, we'll talk about measures and measure spaces. So stay tuned for the next video. And if you liked this presentation on measurable spaces, please don't forget to give it a thumbs up and subscribe so you can find all the videos on measure theory, set theory, and other topics. And if you have any questions, criticisms, or concerns, just leave a comment below. And thank you for watching this video.